Hello everyone and welcome to a new episode of All Things IDA. This is a two-part video series talking about file loaders and processor modules. Today I'm going to be talking about file loaders. The target of this implementation is the CatBert file format. It uses the Piglet VM virtual machine bytecode. Now CatBert is the Mandiant challenge from last month where I also have a video about it, how to solve that CTF. So I'm gonna go over the file format and how to implement a file loader for that embedded Piglet virtual machine in that CatBert files in that challenge. With that, let's get started. Okay, so just some background real quick and a refresher from last time. So this is the video in question where I talk about the CatBert CTF challenge from Flare 11. Now we have here the solution on the GitHub repo of this channel, and we should be able to see the CTF files. You can grab the files. In the files, you should have a bunch of C4TB files. So this is custom format, and we're gonna learn how to load those files into IDA. And then we will be able to write a processor module to disassemble the bytecode in those files. The bytecode in those files are mirrored after this project here. And this project has a headerless assembler for the Piglet file. So we don't have a header. There's no real need to write a file loader for this project directly. But for the CatBert challenge, the PVM files, so this is the assembly code for this virtual machine. In the CatBert, those assembled bytes are not directly in binary form. They're embedded with a header. So we're gonna revisit this header here, how to interpret it, and so on, and where the virtual machine bytes sit, which is basically towards the end. So we're going to write a file loader in IDA that will parse the file, populate the database, and then hand over the logic to a processor module where we can disassemble this. Before I start talking about the implementation of file loader, let me run the whole project and then we're gonna dig deep into the source code. So let me show you how it would look like. So I'm gonna run my project here with IDA. And now what we see here is the CatBert Piglet VM loader. This is what we're gonna discuss today. This is responsible for parsing the file and populating the database. And what we see here is the processor module that knows how to disassemble the files. First, if you're starting from scratch from a file format, a file loader should kick in. If it recognizes the file, it should show in the options. And then after the file loader does its job, the processor module will take it over. So now let me press OK, let the file loader load it, and then the disassembler will be using the Piglet VM processor module. So pressing OK here. The file loader finished, populated the database. So here we have, for example, code section, and here we have memory. And this is the disassembly from that embedded PVM bytecode in that input file. The input file in question is here, catmeme1. The file loader knew how to parse the file and populate the database. And this is coming from the processor module. So let's dig deep into the file loader logic. If we look at the SDK in IDA and go to, for example, any loader example. So here in IDA SDK, we have a subfolder called loader, and we have a bunch of examples we can base our work on. If we follow it here, we'll have the source files, make file, and the needed support files. We can base our work on that. So for example, here, if I open AAF, we'll see just what makes it. Now, if this file format is simple, then the source code of the file loader should be simple. To read the file loader, we can start by looking at the loader_t description block. This is like a plugin. If we take a plugin real quick, let me open a plugin, and I already spoke about plugins before. Plugin is similar instead of having a loader T, a plugin has a plugin underscore T. Similarly, in IDA, a file loader will have a loader underscore T. Loader underscore T is a description block that we should export so that when IDA discovers the file loaders, it will load it, it knows where are the callbacks and so on. So what makes a loader description block? Let's follow the loader underscore T, which is inside loader.hpp. This symbol should be exported. It has version, which we should put IDP interface version. So this is the IDA SDK version. Flags, we can specify loader flags the same way we can specify plugin flags. And then we will have a bunch of callbacks. We'll have the accept file callback, and the responsibility of this callback is to recognize the file or not. It returns an integer where 0 is we don't recognize the file, and non-zero is we recognize the file, and we can combine it with other return flags. So for example, call me again because I recognize this file in multiple formats. This could be, for example, a FAT file format, like macOS FAT binaries, for example, where the same file can have different executables embedded in them and so on. So accept file would return 0 if it doesn't recognize the file, or non-zero plus flags optionally if it recognizes the flag. Its responsibility is accept file is to populate the processor name that this file with loading should be disassembled with, should populate a display name, the file format name. This is also however we want to display it. And this is the file name that we receive. We don't necessarily have to open the file name. We receive an input. This is kind of like abstract object where we can use with other methods to read the input file. We don't have to worry about the input source. It could be coming from memory. It could be coming from the network, could be coming from an archive. We treat the input pointer as a handle with special methods to seek into the input handle, to read, and so on. So accept file, all it does is just simply recognize or not recognize the file and populate the output arguments. The output arguments are the file format, just a string, and the processor module name that is gonna be selected by default to disassemble the input file. If the user, so here, let's really quick run it. So at this point here, we might have multiple candidates that recognize the file. We will always have binary file because binary file here is headerless. But in this case, none of the IDA loaders recognize the input file except our custom loader here, file loader. And once we select the loader, if we accept this one, for example, then IDA will call secondary callback. So in the loader description block, after accept file, if we hit OK in the loading menu, then IDA will say, okay, so go ahead and load the file. It will also give us back the loader input opaque object to give us some options, and it will give us back the same string that we returned to IDA. So we can know if we can handle multiple file formats, the user will select the file format, we will get it back, then the load file will make a comparison on the file format string and change its internal logic how to load that specific file format. So what is the responsibility of loading the file? Load file has a bunch of things to do, but most importantly, it should read the file and populate the database. What does it mean? It means creating segments, reading bytes, adding imports if needed, creating the import segment, adding entry points, caching the fix-up information, and any other metadata we want to capture from the input file and hide in the net nodes. So as well, that depends on your logic, because once we load the file in IDA, we have to assume that the input file is gone. If we ever need something from the input file, our choice was in the load file to take as much information as we need and put it in the database in net nodes, for example. Because again, we don't have access to the input file necessarily after the creation time. And remember, the file loader comes into play only one time. The first time we create a database, the file loader is used. After that, it's not used. Then, after that, it becomes a regular database that's populated, and it's the responsibility of a processor module to actively disassemble and work with the database, but no longer the file loader. So to quickly recap, load file will create segments, copy bytes from the file into the database, create entry points, exports, fix-ups, and whatever else you need to capture and cache. After load file, we have save file callback, which is optional. This helps us do the inverse operation of load file. This helps us convert the database back to a file. So the idea here is to allow us to recreate the file from the database if we wish. We have as well another optional callback, which is move segment. As well, this is called to handle relocations. We have one more last optional callback, which is process archive. This lets us deal with archives. For example, IDA already has archive support, for example, zip files. Let's suppose I have those files for which we are gonna write a loader. Let's suppose they were in a zip file. If I open IDA recognizes the zip file as an archive. Then if I select the archive, I'll have another dialog here showing me the list of files. Then if I select a file from the archive, then I should be able to see the file format. Okay, so let's dig into the source code. We have to know the file format. We can write the parser by hand, we can use a third-party library, etc. This is a very simple file format, which looks like this. So what I'm planning to do is simply simulate a loader for now and show you how I would have done it without writing a file loader. So suppose you don't know how to write a file loader, you know the file format, you can still write even a standalone script to populate the database. So let me do that real quick and then we will be able to match the same logic in the source code. So let's suppose here, I'm gonna load it in IDA without the file loader. It's gonna recognize as binary file. It's gonna assume it's the PC processor module. It doesn't matter which PC mode, so it's not applicable. This is a completely different architecture. So we're just loading the file. If we look at it, I downloaded the file using the binary loader. But file loaders will really hide unnecessary stuff and properly create and populate the database. So if we look at the source code here, this is the header file format. So first signature is 4 bytes. So we're gonna make a DD, press R to highlight it. We can rename this to signature, for example. Here we have data size, and we can also press H to make it decimal. This is how much the encrypted image size is. Followed by the bytecode, position to the bytecode. This is the bytecode pos. And then we have the bytecode size, which is a number. And finally, we have the data as much as data size, and the data size is this much. So we can rename this to data. Make array. Let's make define byte, make array, and this is the data size. After data size, this is followed by, so here at position of the bytecode. So we have to seek to the position to the bytecode, and then we have an array of bytes with the bytecode. So the position here is this one. So we're gonna press G to jump, go here, and here is the bytecode. So I can simply make array bytecode, and it is 601 indeed, goes all the way to the end of the file. This is the bytecode. Our loader, now we're gonna look at the loader. The loader doesn't care really to grab the signature, put it in the database. We don't care about the data. All we really care about is accept the file by verifying the signature, read the bytecode position, seek to it, and populate it into the database. That's all what we want. So let's see that logic. We want to populate only the bytecode here. Let's see that logic in the loader. So the loader descriptor block, let's follow the accept file. We use lread. So lread, among other helper methods, take the input opaque object, and then we can pass that back to read. We don't have to worry about where that input is coming from. We have different loader input types. So for example, here we have local file, we have a remote file backed by the debug server, for example. We have process memory, we have generic as well. These are not for us to worry about. So let's go back to the source code. So here the accept method is very simple. If we don't recognize the signature, we're gonna simply deny the file, just return 0. But if we recognize the signature, we're gonna tell the display name and the preferred processor module. If you haven't implemented processor module yet, you can say meta PC. So let's assume we're just gonna have the PC processor module handle it. And of course, it won't be able to properly disassemble things. So this is accept file, as simple as it goes. Next comes the load file. And load file, one of the responsibilities is to assert again the preferred processor that we want. So here we put the processor short name. I wanted to select the PVM. And again, PVM is just because of the processor module I created and we're gonna cover next time. And so by setting this one here, we're saving it in the database. So set processor type, as opposed to here in the accept file, we're just making it as a suggestion. Like, hey, let the user select. But here, we're really setting it and saving it in the database. So set processor, we set the processor we want. And now we're parsing the header. So if we put this like that and go back to the header, we will see the logic of loading the file. It's seeking to 8, so it's skipping data size. We already verified the signature. We don't need to recheck that again. We're simply loading. So we're seeking to 8 to the position of the bytecode. So QL seek and then read the position to the bytecode. So we're reading where is the bytecode, and then directly we're reading the bytecode size. After we do that, we are ready now to create segments. So what follows is just regular IDA API usages. Like create segment, we could have done it in a plugin. It doesn't have to be in a file loader. So what we're really doing here is creating the code segment. This is up to your program's logic, the loader logic. For example, PE files, the PE file loader chooses to create every PE section in its own IDA segment. And here I chose to create two segments in this loader. One segment representing the memory of the virtual machine. In case we want to create cross references from the bytecode to the memory, I decided to create a segment for the memory. And a code segment for the virtual machine bytecode. So here I'm simply creating or using the boilerplate code to create a segment. And finally we call add segment class code. Then I'm using the file to base API. This API copies the file contents given the input opaque object to the database. This is similar to calling, let's say, patch bytes, for example, or put byte, etc. So this method lets us take the input from a file into the database. I'm using the li opaque object, telling it where to get the bytes we want, where to put it, what's the destination, and what's the end here. So if I follow this one, load portion of a file into the database, input source, position in the file, where to read from, and the EA ranges. IDA will determine how much to read from the file by doing EA2 minus EA1. Then we are responsible for setting the important IDA info. What we need to store in the database using the INF APIs in IDA.hpp. We have so many stuff. This is the database info. We can preset, and usually it's the responsibility of the loader to set those. So for example, what is our starting code segment and instruction pointer? What's our starting EA? What's our minimum and maximum EAs, for example? Then I'm doing the start EA, another segment here for the memory. And I'm not populating it with anything. I'm simply making it as uninitialized bytes. Let's quickly look at the end result here. And segments, we have two segments. We have the code segment. And I chose the base like that on purpose. And I chose to put the memory at starting 0. And this is how big the memory size is for the virtual machine. Here it's BSS and so on. And for the data segment, all I'm doing is just creating a large keyword array. If I press star here and uncheck array, you'll see basically these are all the memory representations. And then I'm setting the big endian versus little endian. So the CatBert seems to be big endian, so I'm just enabling that. Setting the minimum EA as well to the address 0. And here I'm setting the max EA to the end. So basically, the lower address I'm setting it to 0, and the higher address setting it to exactly after how much is the bytecode. And that concludes the file loader. Now, until I implement the processor module, which I did, you won't see any disassembly. But the file loader did this. Then the processor module will allow us to make code. And that's what we're gonna be talking about in the next video. Alright, so that's it for today. What we covered is the mechanics of a file loader, what are the optional and mandatory callbacks, what is the responsibility of the callbacks. Accept file is the first callback we need to implement, and the load file is the second mandatory callback we need to implement. Accept file would recognize the file and tell IDA how to display the recognized name in the UI. And then the load file is responsibility to create the segments and populate the database accordingly and set the appropriate IDA info variables. Alright, so stay tuned for the follow-up video about implementing the processor module. Thank you, and I'll see you next time.